Welcome to Empowered Learning. This is the second video in the video series for vectors and our discussion about vectors in both the two-dimensional and the three-dimensional space. This video is dedicated to doing examples using the knowledge that we learned back in the part 1 video. So example number 1 is asking us to find the component form for the following vectors that will be described to us. So example A is already worked out, but you see that we have some vector PQ where the initial point of the vector is at the point 1, 3. The terminal point is at the point 2, -1. And of course, to build these vectors, we simply just take the difference in the last point minus the first point's components. So we just take the difference in the x values for Q minus P, difference in the x value for Q minus P here. And so when we do that, we see that we end up getting the component, the vector in component form of -4, -1. And so we'll do a similar sort of thing with the other examples that's in this one. So we see here for part B, we have the sum of two vectors. And of course, we're given the initial and terminal points for each one of these vectors. So for our vector AB, we're going to take the difference in between the x value. So 0 minus a -1 will give us a +1. And 2 minus 1 will give us 1 as a result. And I do need to fix that and write it in this form. So this will just be 1 minus 1. If we do the same thing for the vector CD, we see that we have 2 minus 3, which will give us a -1, and we have -2 minus a -1. And of course, if we do the math for that, we end up getting a -1 and a -1 here. Okay, and here this is 2 minus 1, so this should be a +1, not a -1. So we fixed that. All right, so now that we have that, then of course, if we take vector AB and vector CD and we add those together, then we just basically got these two component vectors here. And we know that whenever we add these vectors component-wise, what we can do is just add the x coordinates together, and that'll give us 0. Do the same thing for the y, and that'll give us 0. So this will actually just end up being the 0 vector in 2D space. All right, so for the next example, it's a little different. We want to find the unit vector that makes an angle of -2π/3 radians with the positive x-axis. So if we go ahead and draw Cartesian plane here, and let's say we're going to rotate in a clockwise motion, because negative angles rotate clockwise, to -2π/3, and that is the same as a -120 degrees. And we know that because we know that π/3 in radian world is the same as 60 degree in the angle world. Okay. So, of course, if I multiply that times 2, then that's times 2. And if I make that negative, that's negative. That's how we get a -120. So here we know -120 degrees. If we come in from the positive x-axis, if we spin here, Terminal side of our angle will be here, and we know that this angle inside of here will be 30 degrees, which means this reference angle right here will be 60. Okay, and we'll kind of form it like that. So we want the unit vector, meaning that we want the magnitude of this particular vector here to be 1, and have the terminal side be where we spin clockwise, -2 pi over 3 units. That's where we are. So this looks very similar to a right triangle. Our angle here is 60 degrees. And of course, we are in quadrant 3. So that tells you that this terminal point that's right here is going to have an x and y coordinate that are both negative. If we remember our combinations of sides for right triangles here, using right angle trigonometry, we know that if we have 60 degrees here, that this would be square root of 3 on the side opposite of it, which makes this 30 degrees. This would make this 1. And of course, the hypotenuse here would be 2. Now, since we need this length right here to be 1, we'll divide everything by 2. So this will be divided by 2, divide this by 2, and of course 2 divided by 2 would just be 1. And let's try to fix that here. All right, so we got that together. Okay, so the last thing that we know here is that because of the fact that both the x and y coordinate here have to be negative, we know technically this is, let's try that again. This is a negative here, and this is a negative here. So if we wanted to name this vector v, this would actually end up being a -1/2 here and a negative square root of 3 over 2 here. That's what that particular unit vector will be. And again, we know that it is a unit vector because the magnitude of it is equal to 1. Okay, we forced it to be that, but if we actually wanted to calculate it, we'll see here if we do square root of -1/2 squared plus negative square root of 3 divided by 2 squared. Then of course, -1/2 squared is 1/4. Negative square root of 3 over 2 squared will be a positive 3 over 4. And you see how this ends up being 4 over 4, which that will just be square root of 1, which is just 1. Okay, so we see how that works now. All right, let's move on to example number 2. So in example number 2, what we want to do is take the vectors that are being described here, and we want to write them in its component form, more so the algebraic component form, where we're using the I, J, and K directional unit vectors to do it. Okay? So for starters, we see that we have a vector P1, P2. So we know that P1 is going to be the initial point, and P2 is going to be the terminal point. So we know here, and I'm just going to write it in component form for right now, we know that the quote-unquote x coordinate is going to be the difference in between 2 and 5. The y coordinate is going to be the difference in between 9 and 7. And the z coordinate will be the difference in between -2 and -1. Of course, if we work all that out, we get a -3, 2, and -1. Okay, so if we want to write this in this form, what we'll do is just say now that the vector P1, P2 is just going to be -3 in the I direction plus 2 in the J direction minus 1 in the k direction. For our next example, we see that we have the scalar 5 times a vector u. So basically, we're taking the vector u and we're extending the length of it by a factor of 5. And then we're going to subtract a vector v from it, which means we're going to essentially add a vector that's going to go in the direct opposite direction as the vector v. So to do that, first we need to figure out what 5 times the vector u is, and that's just essentially just going to be, that should be a positive 1 for the y component. So we have this. So that's just going to be 5, 5, negative 5. Of course, for minus v, that's just going to be the direct opposite. It's going to be the vector that has a direct opposite direction of it, which means we'll just multiply all of our components by negative 1. And so finally, we know that 5 times this vector here minus that vector is the same as 5 times this vector plus the negative of vector v. And here we just essentially just look at our components and do what we need to do here. So this will be a 5, 5 minus 5. This is plus negative 2, 0, negative 3. And then we just combine components together. So here, 5 minus 2 will give us 3. 5 plus a negative 2 will give us 3. 5 plus 0 will give us 5. And negative 5 plus negative 3 will give us a negative 8. And that is what our resulting vector would be there. So our last example for example 2 is kind of like the last question that we had in example 1, where we have a unit vector obtained by rotating the vector, the component vector negative 1, 0, 120 degrees about the origin. Okay. So notice here, I've already worked it out. So I look at this vector here and realize that this vector is actually the j unit vector, but the negative of it. So that's actually what it is. So we've taken that and we want to rotate it counterclockwise 120 degrees. So we rotate all the way through quadrant 3 and then 30 degrees into quadrant 4. And so we see that the terminal side of the vector that we're trying to deal with here is in quadrant 4. So that means that my x components will be positive, my y components will be negative. And so using right angle trigonometry again, making sure that the hypotenuse of this right triangle, or if we want to put it another way, the magnitude of this vector here would be 1. We see that across from 60 degrees will be square root of 3 over 2, and across from this understood 30 degrees here would be 1/2. Okay? And so we see that our vector here would just be the component vector 1/2 square root of 3 over 2. And if we wanted to write this in the form that they asked us to, this would just be that this vector, and I'll just call it v here, is going to be 1/2 in the I direction minus square root of 3 over 2 in the j direction. So moving on to example number 3, what we want to do in this example is take the vectors that are given to us in the figure, and we want to see if we can come up with a sketch of what the resultant vector would be. For instance, like part A says, if we add the vector u and the vector v together. So here, we don't have to be precise per se, but we need to just get a general idea of what this is going to look like. So to make this easy for ourselves, one of the things that we know is that if we take the vector u and add it to a vector v, that is the same as taking the vector v and adding it to the vector u. In other words, vector addition is commutative. Well, because of that, we know that I can start off with my vector v, which we see here is flat. So we'll start off here to the vector v. And so now what I need to do is draw a vector u here, okay? And so my vector u is going to start here. It's going to have like a same kind of directional angle, but be shorter, okay? And then from there, the resultant vector is going to be the vector that starts here and ends here, okay? So if I was to draw that, that would roughly look something like this. And we would do that, and this would be the vector u plus v, which is the same as v plus u. And if you wanted to, you could express it this way as well. So in general, that's what that vector would look like, okay? All right, so if we move on to the second example, you see I've already worked that one out. And so we've taken the vector u here, and we said, hey, we have to essentially do the opposite of what vector w looks like. And of course, vector w was going this way, so a vector minus w would, look like that. And so we make it look like this here, and then we attach the tail end of vector minus w to the terminal end of vector u. And so that's what you see here. That point is there. And then, of course, we just draw the resultant for that in the space here. And we see that that vector u minus w looks like what I'm showing you. Okay. All right. So moving on to example C. Now, we know from example A here what the vector u plus vector v is going to look like. It's going to look something like this, okay? So here, one of the things that we can note is that the associative property for vector addition is just like how it is with the real numbers. So we could look at it this way, okay? So again, we know that the result of vector u plus vector v is going to look something like this. So I'm going to draw that. So it roughly looks something, like this. This will be vector u plus vector v. We also remember here that vector w looks exactly like this vector minus w, but turned in the opposite direction. And so I'm going to estimate what that would look like here. Vector w here. And then, of course, to be able to get the resultant vector, what we can do is draw this parallelogram. So I'm going to do that. And so then a resultant vector is just going to be the vector that goes from here to here, okay? And the reason why I've drawn the parallelogram, I'll show you that in just a second. So here, if we was to draw a line, get it to end there and draw that vector, this would actually be the vector u plus v plus w. Okay. Now, the reason why I had drawn the parallelogram here is because of the fact that I could have also taken my vector w and I could have drawn it that way. And if I would have, then this parallelogram would have kind of been like that, and then I would have been able to draw the resultant vector this way. Okay, so no matter how you do it, it still ends up being the same vector with the same magnitude going in the same direction, either way you look at it. All right, let's move on to example 4. So for example 4, what we have here, if we want to determine which position vector shown in this following figure has a given magnitude and direction angle based upon the information that's given. Now, of course, we don't know, we haven't measured this out exactly, but we can kind of guess based upon the information given which one is going to be which. So for example, we know that a vector of magnitude 2 and its directional angle is 90 degrees. Of course, that would be vector D here. Okay. Of course, based upon the positive x-axis, it's rotated 90 degrees and it has a magnitude of 2. This is 1, 2. Okay. So if we're looking and we say, hey, what vector would have a magnitude of 3 and a direction angle of 180 degrees? Well, here we see that vector A here has a length of 3. And of course, with respect to the positive x-axis, that angle is 180. So this would be vector A here. Okay. All right, so if we look at the next one, we see we have magnitude of 3 times square root of 2 and a direction angle of 45. Well, now that one's already worked out. We know that vector E works for that. And of course, we can see here that this looks like it's a 45-degree angle. We can't tell exactly how long that is, but we'll just guess that it's 3 times square root of 2. Now, we see magnitude of 4 and a direction angle of 30 degrees. Out of all of the vectors that we have here, this is the only one that looks like it has a direction angle of 30 degrees, because of course it's got to be smaller than a 45, the direction angle of 45 degrees that we saw for the previous one. So let's try to get that to actually right here. So that's 30 degrees. So F would be the answer for this one. So vector F. And so we also see that we have a vector of magnitude 3 times square root of 2, but its direction angle is 135 degrees. Okay. Well, that's about 45 degrees into quadrant 2 if we are rotating this way. So here, angle C looks like it's the one that would make the most sense for that. Okay. Oh, sorry. Angle B is the one that would make the most sense for that one. And so say that because, of course, this last one here is the one that's 120. And, of course, 135 is more than 120. So B would be the one that would make sense here. C would be, of course, this one here. And the angle going from there to there would be 120. So for example 5, what we want to do is take the information that's given to us about a vector, mainly its magnitude and direction angle, and we want to figure out what are its components. Okay, and so this is something that we'll need to be able to do, to be able to, construct or break down a vector into its components. Whenever we need to do dot product or cross product later on, it's possible that we're going to have to do this sort of thing too. So it's good to be able to figure out what are the horizontal and vertical components for a particular vector. Okay, so if I was to draw, and I'm going to go ahead and do B first, and I'll come back to A. If I was to actually draw out what this looks like, come here. This would be some vector, so directed line segment. This would be like 13.1 degrees here. And this would be the Y x-axis here. And of course, what it is that we're trying to find is well, how much of this force actually is vertical, how much of this force is actually horizontal. And so in looking at this, we know that the horizontal component for it, and I'm just going to call this V sub Y, this is just going to be the magnitude of this vector and cosine of 13.1 degrees. Okay, sorry, I did the horizontal. The vertical component. That's going to be sine. So probably botched that really bad. So I'm doing the vertical component right now, and that's going to be the one with the sine. If I do the horizontal component, that's going to be the one with cosine. Okay. So essentially the magnitude here, this one, we can kind of look at this as the vector going in the Y direction, vector going in the X direction, and of course the magnitude of that is just going to be magnitude of this, which is 6,000. And of course we do sine and cosine deal. Okay. All right. So now that we know what that looks like, I'll go ahead and erase the picture here, and then we'll just go ahead and do those calculations. All right. So now we need to go ahead and make these calculations here. And so this is, we'll just simply put it in our calculators. The main thing we need to remember here is that we need to have our calculator in degree mode, since we're given the angle in degrees. So I'm going to go ahead and press mode, and then just make sure that I am in degree mode. Currently I'm in radian mode. So I'll enter that, then second mode to quit, and then I'll just type in what we're supposed to have. So we know here that the magnitude of the vector V is 6,000. So we'll do 6,000. And then this first one will be sine of 13.1. And that will just be 1,359.9 if we round to one decimal place. And we'll do the same thing over again, but this time use cosine. And plus the cosine, do that. And we see we get 5,843.9 again if we round. Okay. And so that is what our final answers will be for both our vertical and horizontal component here. All right, so now that we've done the calculations, we got the answers written in, we will go ahead and move forward to the next example here, example 6. So for example 6, we want to find the exact magnitude and direction angle to the nearest tenth of a degree for each component vector that we're given here. Okay, so for our first component vector, we see that we have the vector -1 square root of 3. And so just by looking at this, we know that since it's a component vector, its terminal point ends at this particular point on the graph. And we know that x coordinate is negative, y coordinate is positive. So we know that that's going to be a point that is in quadrant 2. So if I was to draw that out, our terminal side here is going to be in quadrant 2. And here, this would be -1. To this would be square root of 3. So this looks like one of those well-known right triangles that we know, 30, 60, 90 triangle to be exact. And so since we have square root of 3 here, we know that this reference angle is 60 degrees. Okay. And that kind of lets us know what we need to know as far as the direction angle is concerned. So the magnitude, now just from knowing what you know about right triangles here, if this side is 1 and that side is square root of 2, then of course this side would have to be 2. But so the answer should be 2, but we can actually calculate it here by doing square root of the x component squared plus the y component squared. And you see here square root of negative 1 squared is 1, and square root of 3 squared is 3. And that ends up giving us square root of 4, and the principal root of 4 is 2. So you see that it actually ends up being that. Our directional angle, we'll call it theta here. Theta is going to be 180 degrees minus our reference angle of 60. And so, of course, that ends up being 120. Now, of course, it could have also just came here and just said, well, to get from here to here, we know we go from this point to this point is 90. And since we got 60 left to get to the negative x-axis, this has to be a 30-degree angle in here. So we could have did that way as well. All right, so for part B, we can look at this and easily tell here that the magnitude of this particular vector is going to be 6. And we know that because if we draw this vector, this is going to be on the negative y-axis here. Okay, we can do the calculations, but common sense just tells you that's what it is. So if I'm here, and let me switch colors here. So if we had this vector going down like this, then of course this is the vector 0, minus 6. And of course the length of that vector is 6. Okay, so we know from here the length of this vector is 6 just by looking at it. And the directional angle, if we start from here and rotate, we know that that's going to be 270 degrees because we got 90 plus another 90 plus another 90. And 90 times 3 is 270. That slipped. So we'll try that again. Okay, so that is what example B answers would end up being. So if we do example C, you see that it's already worked out. So the magnitude of this particular vector, we would just take the square the components, add them, and then take the square root of that result. And you see here we end up getting 2 times square root of 10 for that. Our directional angle, since we know that the terminal point for this particular component vector will be here, and points that have positive x values but negative y values are going to lie in quadrant 4. So that means our angle will be in quadrant 4. And so I've drawn that here. And of course, if we do the whole right triangle thing for that, we see that we end up having to essentially find out what theta is by taking 360 and subtracting this reference angle alpha from it. And of course, alpha, since it's a reference angle, it is by definition an acute angle. And that is just like if we were in quadrant 1 and I was asking you, what is alpha here? Okay. And so of course we would say, to find out what alpha is, we would say tan inverse of 6 divided by 2 here. Okay. So that's where that arctan or tangent inverse of 3 comes from. because that's just essentially what alpha is. Of course, we put that in our calculator, making sure that we're in degree mode, and we get 288.4 degrees is our directional angle. So for example number 7, we are asked to express each vector that we're given as a product of its length and direction. So I went over this in the part 1 video for this. Essentially, we're just trying to rewrite this to where once we find the unit vector, we're going to write this vector as a linear combination of the unit vector. And what that's going to look like is a scalar value, which is going to represent its length, times the actual unit vector. And so here we know that the length of our vector is going to just be the magnitude of it. Direction of it is just going to be the unit vector, which is just the vector divided by its magnitude. Okay. So the first thing that we need to find out is what is the magnitude of this vector. Okay. So of course, since this is a vector that is in 3D space, we'll say square root of the x component squared plus the y component squared plus the z component squared. And this will just be square root of 4 plus 1 plus 4, which is square root of 9, and that is just 3. So we know what our magnitude is. Our unit vector now is just going to be this vector divided by the magnitude. So we'll have vector divided by the magnitude. I'll go ahead and write that out. And all this is divided by 3. So we have 2/3 times unit vector in the x direction. And then we'll have plus 1/3 j direction unit vector minus 2/3 k direction unit vector. And so now that we have that, we know, and this is really just a play on algebra here, that our vector can be expressed as the magnitude of vector u times the unit vector. Okay. And so of course our magnitude or length of vector u is going to be 3. And that will be times this vector here. Of course, we want to leave it in that form because now we have everything expressed in terms of length here, and of course, direction here. So for example B, we see that we want to do the same thing, but notice here that we only have I component and a k component, meaning that this vector is only built in the I direction, only has components in the I direction and the k direction, or it only has x and z components. Okay, so here we just calculate the magnitude. It's just going to be 3/5 squared plus 4/5 squared, and then we take the square root of that. Of course, 3/5 squared is going to be 9/25. 4/5 squared is going to be 16/25. And if we add that, we end up getting 25/25. And of course, that just ends up being 1. So the good thing about what we've just found out here is that we already have our answer, okay? Because if we look at this, the vector that we're looking at is itself the unit vector. So we know that the unit vector can be written as 1 times itself. Okay. So all we have to do is this, and we're done, because we already know what the magnitude is. Since this has a magnitude of 1, it is a unit vector, so this vector tells its own direction. Okay. All right, so for example C, we have one where we have a vector that has an I, J, and K component, which means it's built with components that are going in the X, Y, and Z direction. So here we remind ourselves that a vector U can be written as its magnitude times the unit vector. And of course, we just take the square of all the components, add them up, and then take the square root of it. We get 1/4 here. And then we take our unit vector, which is just our original vector divided by 1/4, which is the same thing as taking our unit vector and multiplying it times 4. And we see that we get this outcome here. And then to rewrite everything as the length of the vector times the unit vector, we would just say 1/4, because that is what the magnitude of the vector was, times the direction of it, which we found here. All right, so let's move on to example 8. So in example 8, we're kind of doing the opposite of what we did with example 7. In example 7, we had a vector, and what we wanted to do is break it down into its product of its length and direction. What we want to do here is, given the length and the direction, figure out what the vector is going to be. Okay. Now for this first one, it's pretty easy. We know that the J directional vector itself is just going to be 0, 1, 0 when it's in its component form, but the minus of that will make that 1 here be negative. And of course, if I take any unit vector and multiply it times its length, that would give me, a regular vector. And so here, if I just multiply square root of 7 times all 3 terms here, all I'll get is this. And of course, what this really is, if we want to write it in algebraic terms, is just going to be a negative square root of 7 in the J direction. Okay. So we could have just simply wrote this as this to begin with. Now, for this next vector, it's called vector V. We want to do the magnitude of it times the unit vector for it. And of course, since this is the direction, we automatically know that it is, by definition, a unit vector. So all we have to do is multiply this 1/12 times this vector here. Okay. So this would be 3/5 in the I direction minus 4/5 in the K direction. And if I multiply 1/12 times 3/5, I know that the 3 goes into 12 4 times. So what I just end up having here is 1 divided by 4 times 5 in the I direction. And I know that this 4 goes into 12 3 times. So I would have minus 1/3 times 5 in the K direction. And if I work that all out, then I end up getting 1/20 in the I direction minus 1/15 in the K direction. For example C, again, all we need to do is take the length and multiply it times the unit vector here. So if I do that, then I just have 13/12 times 3/13 in the I direction minus 4/13 in the J direction minus 12/13 in the K direction. And of course, if I multiply the first term here, the 13s will reduce to 1. And I'll just have 3/12 I. And of course, that's going to reduce to 1/4, but we'll take care of that in the next step. Multiply times the second term. Again, the 13s will reduce to 1. And I'll have 4/12j. And then doing it in the last term, 13/12 and 12/13 are reciprocals of each other. So it'll just end up getting 1. And we're just left with minus k in that third term. And of course, 3/12 is the same as 1/4. And 4/12 is the same as 1/3. And we see that our vector v ends up just being 1/4 I minus 1/3 j minus k. All right, so for example D, which is our last example for example 8, here we're given a general, I guess, description of the length. We're just saying, hey, if the length is some scalar value a, and a is positive, and we know the direction, what is the vector going to look like? And essentially, I wrote a lot here, but essentially all it is we're just taking a and we're multiplying it times each of these terms here, so that's what we'll end up getting. Okay. So for example 9, we know how to do a problem like this. We're just putting some context to a problem type that we've already done. But of course, we're going to have to learn some new vocabulary here. So we have an airplane that is flying in the direction of 25 degrees west of north. And so if I was to draw that, if I considered the positive y-axis north and the positive x-axis east, then flying 25 degrees west of north would look like this. Right? This would be 25 degrees here. Okay. Now, we're told that the magnitude of this particular vector here is 800 kilometers per hour. So this is a rate. And what we want to do is find the velocity. We want to find the component form of the velocity of the airplane. Okay. So what we basically want to do is to say, hey, we have this vector here, but let's break that vector down into components. Mainly the component, the velocity of the plane that's contributing to it going due west, and the velocity that's contributing to the plane going due north. Okay. So for here, we know that since we have 25 degrees in between the positive y-axis and the terminal side here, we know that the difference in between the negative x-axis and the terminal side is just going to be 90 minus whatever, 90 minus 25. Okay, so we're just doing that. And of course, that ends up being 65. So 65 degrees. We could form a right triangle here. And now, if we go back to what we remember about breaking down a vector into its vertical and horizontal components, I'll switch colors here just to make that more pronounced. This is going to be the vector that's going to be in the x direction, and this is going to be the vector that is in the y direction. Okay, and what we're concerned about is the magnitude of these two vectors. Okay, so we know that the magnitude of the horizontal component vector, that is going to be 800, because that's the magnitude of the actual vector itself. And this is going to be cosine of 65 degrees. Okay. Now, another thing I need to note is that since our vector, which also doubles as the terminal side of the directional angle, that goes from here to here, since that's in quadrant 2, we know that this result is going to be negative. Okay, so here I can put a negative here and a negative there, because I know, again, in quadrant 2, the x coordinates for a point, and thus the magnitude for this particular vector, so not the magnitude, but the direction in which it's going is going to be negative. Okay, so that is what our horizontal component would be here. Our vertical component, since y values are positive in quadrant 2, it's going to be a positive value, and this will just be 800 sine of 65 degrees. And my pen just went haywire. Right. And so here, all we need to do is put these values in our calculator and figure out what the corresponding values would be here. So go ahead and bring this in, and we'll just say 800 cosine of 65 degrees. And I'll check to make sure that I am in degree mode. And that's going to be 338.09. We'll just round it off the 0.1. And do the same thing for vertical component. And that'll be 725. But again, we know that for the vertical component it's going to be positive, but for the horizontal component it's going to be negative. Okay, so we'll go ahead and write that in now. So this will be a negative 338.1, and this will be kilometers per hour. And we have a positive 725 kilometers per hour. So for example number 10, what we have here is a traditional statics problem. And so for those of you that are engineers, especially mechanical engineers or civil engineers, you may be watching this video, you know all about this. Okay, basically statics is the study of structures to where everything is in place. So there's no forces moving, so everything is sort of balanced out so nothing falls. Of course, dynamics is the study of structures and things where forces is actually moving. So here we have a situation where we have a weight hanging on 2 wires, and these 2 wires are connected to let's say some type of wall or other structure to where it's just hanging. Okay, and so what we want to do is figure out, in this case, what is going to be the magnitude of force. Let's see. So we have the magnitude of force 2 already. So what we want to do is find out what is going to be the magnitude of force 1. So we need to know what this is, and we need to know what this actual weight is. Okay. So what I've done here is I've expressed everything in terms of what I call horizontal balance and vertical balance equations. If I use physics terms, I'm basically doing a free body diagram where I'm separating all the forces that are going in the positive and negative y direction, writing that as one equation, and all the forces that are going in the positive and negative x direction, writing that as one equation. And of course, the sum of all those forces would have to equal 0. Okay, so if I did a free body diagram for this, then of course vertically I would have my weight down here. The force that I would have coming up here would actually be a combination of 2 forces. Okay, and so that first force would be the magnitude of F of 2, and it would be, there's two ways I could describe it, but since I have this angle here, I know that if I look across from that and I wanted to figure out what this side was, I could do sine of 35 degrees, okay? So I could express this as sine of 35 degrees, okay? Or what I could do, so the other thing I could do here is I know that this could be 55 degrees here, and I could calculate this side as being the magnitude of f of 2 cosine of 55, okay? But since it was already given, I was already given that angle, I just used that, okay? So I have that plus the force that would be contributed by the force F1, okay? So here, across from 40, I could do the magnitude of F1 sine of 40 degrees, okay? And so from a vertical standpoint, the sum of these two forces must equal the sum of, the sum of these two forces must equal the weight of the actual weight that's suspended here, okay? Now, if I look at this vertically now, I got forces acting in this direction, forces acting in that direction. And to get those forces, got forces that's acting this way, forces that's acting that way. And on the left-hand side, I have the magnitude of force F1, and this would be cosine of 40 degrees. And the reason it'll be cosine is because we see that we have this angle 40 here, and we have alternate interior angles, so this angle would also be 40, okay? Similarly, since this angle is 35, this angle would be 35 degrees as well, okay? And so it's for that reason that on the positive x-axis side, I would have magnitude of force F2 times cosine of 35 degrees, okay? And these two forces here, of course, if I added them, they would have to end up being 0, okay? And so these horizontal and vertical balance equations that I have, that's essentially where they come from, okay? So for the horizontal one here, notice that if I put everything on one side, then I'm looking at this force on the left side as being negative, and the force magnitude of f of 2 cosine of 35 as being positive, and I would have that equal 0. Of course, if I was to add magnitude of f of 1 cosine of 40 on both sides, I have this, and then I solve for the one thing that I don't know. That would be magnitude of force F1. And of course, that's roughly about 106.9 newtons. So now, for the vertical balance equation, I take the sum of these two forces here, what's going vertically, both contributing from force F1 and F2, and I know that has to be equal to the weight itself. And I was given F2 to be 100, and I found F1 to be 106.9 roughly. So all we do is have to substitute that in, do the math, multiplying it times the various cosine functions, and we see that the weight approximately weighs about 126.1 newtons. Okay. All right, so example number 10 was relatively easy to do. If we look at example number 11, this one will be a little bit more involved, so that's why I actually wanted to work this one out. But the principle is pretty much the same, okay? So we see here that we have a 50 Newton weight suspended by 2 wires as shown. The magnitude of the vector F1 is going to be 35 newtons, okay? And what we want to do is find out what is going to be this angle here and the magnitude of vector F2, okay? So just like we did before, we need to find out what is going to be our horizontal force balance equation and vertical force balance equation. And so we'll do the horizontal one first. So horizontal balance equation. So here, if I'm looking at this, I got forces going in a positive and negative x direction. So I know that in the negative x direction here, I have the force of magnitude of f of 1 cosine of whatever alpha is. Because again, these are alternate interior angles. On the other side, I have magnitude of force F2, and this will be cosine of 60. Okay. And so because of the fact that this force on the left side is considered to be negative, I'll go ahead and put a minus there. And we're just going to say here that minus force on the left side plus the force on the right side. Those two things would have to equal 0. Okay? And essentially what this means here is that let's try to clean that up here. So we got the magnitude of force F2 cosine of 60 going to equal magnitude of force F1 cosine of alpha. And so here we remind ourselves that F1 is 35 newtons. And of course, if we use our right angle trigonometry here, this is 60 degrees and this is a right angle. This is square root of 3. This is 2. That's 1. And so cosine of 60 degrees would just be 1/2. Okay. So working that out now, if we multiply both sides of this particular equation by 2, let's say if I multiply this by 2, then what I would essentially get here is that the magnitude of force F2 is going to be equal to 70 times cosine of alpha. Okay. And so we'll keep that in mind because we'll probably need to use that later. Okay. And let me actually need to do all of this. Okay. All right. So that's our horizontal balance equation. That's what that yields us. So now we're going to do the same thing, but look at the forces vertically and balance those out. So we have our vertical balance equation. So if we look here from a vertical standpoint, we know that in the positive y direction, we're going to have a sum of the component of both the force F1 and F2. So this will be magnitude of F1. And of course here, this angle is across from this side here. So that's going to be sine of alpha. And we'll add to that the magnitude of force 2. And this is going to be, should be sine of 60, not cosine. So this is sine of 60 degrees here. And again, that's because we know sine is going to be opposite over hypotenuse. Okay. And so we know that the forces going up has to balance with the forces going down. So here I'm just going to say it equals 50. Okay. Now we know that our force F, magnitude of force F1, we know that that's 35. We also know that our magnitude of force F2, this is actually 70 cosine of alpha. And we know from here that sine of 60 degrees is going to be square root of 3 over 2. So from that, we could simplify this equation a little bit more. And so this means here that we have 35 sine of alpha plus 70 divided by 2 is going to be 35. And then times square root of 3. And then that will be cosine of alpha. And then that would equal 50. Okay. So now at this point, we're thinking, all right, well, how could we, simplify this? Okay. Now, if you remember from trigonometry, one of the things that was taught, may not remember this, but one of the things that was taught was that anytime we have a sum of sine and cosine functions with coefficients in front of it, we could rewrite that as either a function of just sine with some phase angle or a function of cosine with some phase angle. Okay? And so what we want to do is get this into a form that's easiest for us to deal with that and then make that transition. Okay? Now, another way that we could actually do this, which to me is a little bit more difficult, but it just really depends. We could get everything except for one term on one side and then square both sides. And if we do that, then we basically turned our equation into a quadratic equation. And of course, the caveat there is that you're going to have to use some trig identities, mainly the reduction formulas, to be able to rearrange and get what it is that you want to get. Okay. And so I prefer to actually use the transition from taking a sum of sine and cosine functions to one that just looks like a cosine function with some phase angle. To me, that's a lot easier to remember than trying to do all the other stuff. Even though I could do it either way, I just prefer to do less steps. So, all right. So to do this, I notice here that this is 35 and this is 35 times square root of 3. So if I divide both sides by 35, then what I'm going to have here is sine of alpha plus square root of 3 of cosine of alpha equals 50 over 35. Okay. Now, the reason I wanted to do that is because I know just from my right triangle up here, if I have a vector whose terminal point looks like something to where one of the components is 1 and the other is square root of 3, then I know that the right angle trigonometry here is going to say, well, hey, guess what? my phase angle for this is either going to be 60 degrees or 30 degrees. Okay. And so I want to use what I already know to my advantage there. So here, what this means for me is that I'm going to rewrite this as square root of 3 cosine alpha plus 1 sine of alpha. And of course, if I simplify 50 divided by 35, that's going to be 10 divided by 7. Okay. So now at this point, let's go ahead and recite the conversion from a sum of cosine and sine functions to just a function of, in this case, cosine. We could do either or, but changing it to a function of purely cosine is easy. So I'll say recall that if we take, and that should be cosine first. So we do a cosine of alpha plus b sine of alpha. This is going to be equal to big A cosine of whatever our angle is. And in this case, this will be minus some phase angle beta. Okay. And how we translate this, and I'm going to draw it out so that it's easy to see here. This is some point AB, and this is the terminal point for this vector. This vector will go here to the origin, and beta would be that phase angle. Okay. And so we see from that if we form a right triangle here, then of course tangent of beta is going to be b over a. And so that's essentially how we're going to find that directional, sorry, not the directional angle, but the phase shift that we need in order to make all this work. Okay. So we know that this phase angle here is going to be found by tangent, and of course we need to make sure that we understand what quadrant we're in, because we may have to do some adjustments to that. And a is just going to be square root of a squared plus b squared. So basically the x and y components, we square both of them, add them together, and take the square root. Okay. And here I'll just restate this again. And of course we'll have to know what quadrant we're in. And according to these values here, this is A and that's B. We're going to be in quadrant 1, so I've actually drawn this correctly. Okay. All right, so now all we have to do is calculate what it is that we know, and then switch this into some number cosine of alpha minus some angle. Okay. So here we have square root of 3 squared plus 1 squared. And that's just going to be 3 plus 1 squared, which is square root of 4, which is 2. So we know our A is 2. And that's just the amplitude of our cosine wave that we'll have. So to find out our angle, we see here that because of the fact that we are going to have our A is square root of 3 and our B is 1, we know that the hypotenuse of this is 2, and this is a 30-60-90 triangle where this angle beta here would be 30 degrees. So even though I could use this particular formula here, since the A and the B worked out to be nice and easy, I'm just going to avoid that and just say, all right, well, beta here is 30 degrees. All right, so in my next steps, what I'm going to do to keep the math a little bit more simple, because of the fact that this answer, we have to give this answer in degrees, I'm going to keep my phase angle beta in degrees, okay? Normally what I would do is I would change this to radians, because that would be the proper thing to do, because we're dealing with, we got other terms in there that have real numbers that it needs to deal with. But just to keep it simple, I'm going to keep everything in degrees here. So this means now that, and let me switch colors here so that we see something has changed. All right, so therefore, we know that square root of 3 cosine of alpha plus 1 sine of alpha. Yeah, that got away from me there. Sine of alpha equals 10 over 7. That implies that this left-hand side could be rewritten now as A, which is 2, cosine of alpha minus, and then beta is going to be 30 degrees. And that is going to be equal to 10 divided by 7. All right, so we are on our way to the finish line here. So now what I need to do is just solve for what alpha is. So the first thing that I could do is divide both sides of this particular equation by 2. And if I do that, I'll just get cosine of alpha minus 30 degrees. And that will be equal to 10 over 14. 10 over 14 is the same as 5 over 7. Okay. And of course, from there, since this number 5 over 7 is positive, I know that when I do the cosine inverse to find the angle alpha minus 30, that particular angle is going to be in quadrant 1. Okay. So I know that alpha minus 30 degrees is going to be cosine inverse of 5 over 7. And so, of course, what that tells me is that alpha is going to be 30 degrees plus cosine inverse of 5 over 7. Of course, from here, all I need to do at this point is use my calculator to get the final answer here. And I'll go ahead and bring that in and do that. So here, again, my calculator is in degree mode. So I'll just type in 30 plus, and then cosine inverse of 5 divided by 7. Enter, and we see that we get roughly 74.4 degrees. So here's 74.4 degrees, and that is what our alpha will be. Okay. So now that we know what our alpha is, we can now also calculate the force that was missing here. And the force that was missing here, if we go back, I believe was, the force of F2. So now we can calculate this. So here, therefore, we know that the magnitude of force F2 is just going to be 70 times cosine of this 74.4 degrees here. So what I'll do is just use the actual angle, and I'll say now let's do 70 cosine of what our actual answer was up there, and that's just to keep the accuracy of the answer here. And we see that is going to be roughly 18.8. Okay. And I should actually be doing this here. So this would be approximate, and this would be approximately 18.8. And since this question, we were talking about newtons here, this would be in newtons. So these would be our two answers there. And so this is how we would solve a problem like this. Of course, basic engineering problem, especially if you're a mechanical or civil engineer, but you see how using vectors and using that concept, how we use that to be able to solve these types of problems. All right, so this concludes the part 2 video on vectors. We're done with the example video. I hope that this helped to bring some clarity for those of you that watch it. Take care.